Hey guys, welcome back. This is going to be the AP Circuit Notes Part 5. We're going to go over some of the components we're going to need to build circuits with in person. The first thing is we're going to have light emitting diodes. So these only allow current to go in one direction. They block it in the other direction. That's exactly what a diode is. The positive side is going to be this side. The negative side is going to be that way. So my current is allowed to go this way. These little lines here represent photons. I tell you that it's giving off light. The actual component, one of the legs is going to be longer, and that's going to be your positive. What we use this for is to tell that we have a closed circuit, that we have a complete circuit. So we use these for all sorts of things. Right now I'm looking at the laptop, and there's a little LED that tells me that my camera's on. If you have a computer or a television, you look at the light in front of it, it tells you that it's on. So the LED tells you have a functioning circuit. These are best viewed straight down. So you're looking at it straight down. So looking at it sideways isn't going to be a good way to tell whether your LED is lit or not. These work by electroluminescence. So it's a very specific energy drop that an electron goes down and gives off a specific wavelength of light that's equal to a certain energy. Later in the year, after the AP test, we'll do a lab where I relate those two together. We're also going to have wires. Wires are just meant for us to connect one component to another. We're going to have a battery clip, and on the battery clip, the red one is your positive, and your black one is your negative. And that's universal as far as circuits go. All right, so instead of soldering or twisting the wires together or connecting them in other ways, we're going to have a breadboard. So inside of here, where you can't see, inside those little holes are two metal springs. And if you put something in there, it'll be held in place by those metal springs. They connect to the ones that are next to them. So these, along the outside, all of these are connected to each other, and those are all connected to each other down the end. In the middle here, where we're going to do most of our work, usually you just connect the battery to the outside ones. These 5 are connected, these 5 are connected, these 5 are connected going down that way. So the idea is that if I run a component from here to that row, I can put one in that one to there, and now since this one and this one are in the same row, these are connected. You actually don't have to touch the wire, so you can have up to 5 things that are connected in one single row. And you can also just pull them easily out because a spring holds them in. They're known as breadboards because they look exactly like a piece of bread. The switch is not easy to take out, so please leave it in. It should just be in one specific spot for all of our experiments that we do. And it's a little push button one, so you push the button and it connects a little lead inside of it. You're going to have a variable resistor. A variable resistor has 3 legs on it. Only 2 of them are necessary. You're always going to use this one, and then you'll use this one or that one. And you'll have a little twist dial so we can change. And we'll use that to see how our relationship between resistance and brightness is. Explain why birds can sit on power lines safely even though the wires have no insulation around them. Both of the bird's legs are at the same potential. Charge is only going to flow if there's a difference in potential, as opposed to a ladder that's touching a hot wire that goes down to the ground. The ground is at a different potential than the wire. different lamps might have batteries connected in either of the two arrangements. What would be the advantage to each scheme? This would make it brighter because you have more potential, more push. This would last longer. So it might be dimmer, but it might last longer. Given the circuit shown in figure 1938, use the words increases, decreases, or stays the same to complete the following statements. If R7 increases, the potential difference between A and E would stay the same, because changing this isn't going to change. Potential difference between A and E is the value of this battery, right? If R7 increases, the potential difference between A and E, if they're saying that there's an internal resistance in this, then all right, so if there is a potential difference, then if this one has a bigger resistance, it's going to get more potential. So that means that this one is going to get less, so it would decrease. If R7 increases, the voltage drop across R4 is going to decrease. It's going to get more of the overall voltage drop. If R2 decreases, the current through R1, so by decreasing this, I'm going to decrease the total resistance, which would increase the total current, which would increase the current through R1. If R2 decreases, the current through R6 is also going to increase. If R2 decreases, the current through R3 would increase. So if it's, no, this would decrease. So more is going to go this way, so less is going to go that way. If R5 increases, the voltage drop across R2. So as this gets bigger, that's going to make this overall path have a bigger voltage. That means that this voltage drop is going to be less. If this gets bigger, that's going to make the overall voltage drop bigger. So R4 is going to get bigger. And if R2, R5, and R7 increase, that's going to stay the same because it's just the battery, right? The battery is the battery. All right, resistors are connected in series when there are no, what am I looking at here? Okay, all right, which is the circuits shown in figure 1940 are resistors connected in series. Resistors connected in series means there is one path. So we're going to have A and C. 2, which resistors in figure 1941 are connected in parallel? R1 and R3 are. R2 is actually in series with V2. A 10,000 ohm resistor is placed in series with a 100 ohm resistor. The current in the 10 ohm resistor is 10 amps. The resistor is swapped. How much current flows through the same? It's still going to be the same. So that's going to depend on the total resistance, and you're not changing it. So the order of things is not going to affect how much current something gets in series. They're all going to have the same. And it's also not going to affect the voltage drop across the resistor. It doesn't matter what resistor's first. The bigger resistor in series will get the bigger voltage drop. 2 identical 10-volt batteries and 2 identical 10-ohm resistors are placed in series, as shown in 1942. If a 10-ohm light bulb is connected between the batteries and the other end between the resistors, how much current will flow through the light bulb. It looks like none's gonna. Yeah, there's not gonna be any that is gonna flow through it. There'd be a 5-volt drop, or half a drop there and a half a drop there, but this difference between the potential there and there is nothing, so you're not gonna have anything flow through. Which resistor shown in 1943 has the greatest current going through it? Assume that all the resistors are equal. So R5 is going to have the biggest one. So when we combine those, the total resistance of these two together is going to be less than the total resistance of those two, which means these three from here to here is going to be a bigger voltage drop than there to there, and this gets all of it. So R5 is going to have the biggest voltage drop, and V equals IR. Figure 1944 shows 3 identical bulbs in a circuit. What happens to the brightness of bulb A if you replace bulb B with a short circuit? It's actually going to get dimmer, because by taking this out, you actually increased the overall resistance. Oh, I'm sorry. They're asking about bulb A, not about bulb C. Bulb A would go out. There would be no reason for any of the current to go through bulb A. If it can go through a wire. We take a wire to have zero resistance, right, in a circuit. When a switch shown in figure 1945 is closed, what will happen to the voltage across R4? By closing this, I'm adding another parallel path that's going to make the overall resistance of this together less, which means there's going to be a bigger voltage drop across R1, which means the voltage drop for each one of these is going to decrease. So R1 is going to increase, I just said. All right. I'm going to move through these because we don't have to worry about capacitors. All right, so it's possible that you will encounter a circuit that cannot be broken down into series and parallel connections. And this happens often when you have multiple batteries. Because of this, we can use Kirchhoff's loop rules. So Gustav Kirchhoff was a contemporary of George Ohm, and he devised these rules for DC circuits. And they're based on a couple basic facts that we've been using already to solve problems. One, all the voltage needs to get used up in a total loop. So the voltage drop across an entire loop around a circuit is 0. And 2, current, which is the charge per unit second, right, has to be conserved. So the amount of charge that is going into a junction has to be equal to the amount of charge that's going out of a junction. So charge does not get used up. Current does not get used up. All right, so at any junction, all of our current is accounted for. So our I total equals I1 plus I2. So the sum of the currents entering a junction equals the amount going out. So in this case, it would be I3 equals I1 plus I2. So I3 is entering the junction A. Some goes up, some goes down. Those two together have to be equal to the original one. Number 2, the sum of the voltages around a loop is 0. So when we go all the way around, all of the potential of a battery needs to be used up. All right, so let us start at D. When I go in the right direction across a battery, I gain 12 volts of potential. This corresponds with this. That's from D to E. Now I'm going to go from E to A. A wire has 0 ohm resistance, so that means that my voltage stays at 12. Now I'm going to go across a resistor from A to B. When I go across a resistor, I have a voltage drop. That voltage drop is equal to minus IR. That's what the equation derived from Ohm's law tells us. And so in this case, my drop is 7 volts. So I go from 12 down to 5. Then I'm going across another resistor. So I have another voltage drop, which is minus IR, which they're telling us is 5 volts. And then my final path, I go through a wire that has 0 ohms. So minus IR is going to be minus nothing. I'm at 0. So if we go forward across a battery, add the 12 volts. If you go backwards across it, you would subtract it. Going across a resistor, you do minus IR. All right, so we're going to try to make it into one loop, and we're going to choose the direction of the current. The current is going to go from positive to negative. This is our conventional current. And a stronger battery is going to win. So if two batteries are pushing against each other and one's 20 volts and one's 12 volts, the 20-volt battery is going to overpower the 12-volt battery. You're going to follow it in the loop you choose. If we cross a resistor, we're going to do minus IR. If we cross a battery in the direction of the current, we're going to add the voltage. If we cross the battery in the opposite direction of the current, we're going to subtract the voltage. And then we set each of the loops equal to 0. All right, so the first thing that I'm going to do is get rid of this. I'm going to combine those, and I'm going to say that those two resistors could be replaced with one resistor that would be equal to 1 over 400 ohms. 1 over 400 ohms plus 1 over 300 ohms, and that is 171. And now I'm going to start someplace. Doesn't matter where. I'm going to start here. And in this case, I go across a battery, so I'm going to add 9 volts. So I'm going to add plus 9 volts. I'll do here. I go across a resistor. I'm going to do minus I times 171. Now I'm going backwards across a battery. I'm going to do minus 1.5. Then I'm going across a resistor, minus I times 100. And then finally going across the second resistor, which is going to be minus I times 200, and that's going to be equal to 0. So I'm going to have 7.5 volts on one side, and I can combine all of my I's together. So I have 200 plus 100 plus 171, which would be negative 471I, and add that to the other side. And then I can get my current as being 7.5 divided by 471. So 0.06. This can become more complicated and more cumbersome. I'm going to go back and show you just what that would look like with the example that from your book. AP has never had you guys make it that complicated. But we could do this one. because we have two different loops. So we know this relationship too, so this will hold true. So that's an equation. Three unknowns in one equation. So if I have three unknowns, I'm going to have three equations. I'll start at D, and I'll go across the 45 volts. And so I'm going to have plus 45. I'm going across the resistor. So minus I times 1 minus another resistor. And I got to label what my I is, which is going to be minus 40 times I3. Then for this one, I'll go up. And so now I have I1. I'm going to go across this resistor, minus 30 I1. And then I'm back to there is equal to 0. So my first equation is 45 minus 41 I3 minus 30 I1 is equal to 0. And then I can do the same thing, but now I'm going to go down. And so I'm going to have 45 minus, I'm still going to have I3 and minus 40 I3. So minus 41 I3. Now I go down, and this is I2. And I'm going from the negative to the positive, so this is helping me. So I'm going to have to add 80 and then subtract 1 I2 and then subtract 20 I2s. So minus 21 I2 is equal to 0. And so I have three equations and three unknowns. This is solvable. There's not enough time on the test for you guys to have to do that. I use the rules for the loop. All right, so I'll give you guys a chance to try this on your own, see what you think the current is. And so you should have gotten a current that was equal to 0.03 amperes. So we could start anywhere. My current is going to flow this direction because the 6 is going to overpower the 3. I'll start here. And I'm going to have plus 6 minus 50I minus 3, because I'm going backwards across this battery, minus 30I minus 20I is equal to 0. So I have 3 on this side and minus 50I. So I would have 3 equals 100I. So I is going to be 3 over 100 or 0.03 amperes. It turns out that I want to scroll that so it's not clear. Slide all this stuff down. Realistically, for us to have a circuit, something has to be providing this potential difference. Faraday called this an EMF, which I don't like it, but we still use it. EMF stands for electromotive force. Sometimes they'll tell you that it's just a battery and it doesn't have an internal resistance. Realistically, in real life, batteries do have internal resistances. And so the voltage that you get from them, the potential you get from them, is going to be this EMF minus the amount of voltage you lose from the internal resistance. And this is known as the terminal voltage. Keep in mind, because this is whatever the battery says it is minus IR, the terminal voltage will change based on how big your current is. The internal resistance of the batteries we would take to be constant. So I have a 12-volt battery, and in reality, I have a 12-volt battery that has a 0.5 ohm internal resistance. If I have 2 amperes coming out of this, my terminal voltage is going to be this 12 volts minus IR. So it would be 2 amps times 0.4 ohms, or 11 volts. This has also not ever shown up on the AP test with the idea of a terminal voltage.